Welcome, fellow practitioners of physics, to the beginning of our mechanics topic and with our first lesson, motion. Now, you're probably asking yourself in your head, all the other videos have been inside. Why is this one outside? Why did you take me into the outdoors? I'm an indoor person. And my answer for that is to demonstrate the motion. Look around. That moss on that tree, actually it's Spanish moss, but who cares? This grass, the wind, it's all moving. It all represents motion. Everything in this world moves, which was what makes motion such an integral topic to mechanics and to physics. So buckle up and get ready to dive right into this wacky world with all its wonderful, wonderful equations. So, with motion, there are several key concepts that you first must understand, the first of which being displacement and distance. Now, I've talked about displacement and distance plenty of times before, so I'm just going to do a brief rehash of it. Distance is simply how far you went from A to B. So how far from point A to point B. While displacement is the shortest distance from A to B. Both are measured in meters, that little m, but while distance is scalar with just a magnitude, displacement is a vector, possessing both magnitude and direction. A favorite example that I've used before and I will use again is if you're traveling around in a circle. Your distance is going to be, if you travel from point A to point B, you travel one full circuit, your distance is going to be the circumference of the circle, while your displacement will be zero, because the shortest distance from one point to itself is nothing, and thusly you have no displacement. So, that pretty much covers displacement. So now we're going to get a bit more complicated. We're going to add in time, because time is a pretty integral part of physics. I mean, literally, the world we live in is a space-time fabric. Time is literally one half of it. And thusly, we will now take our distance, which is most often represented by the variable of s, so I'm just going to use the variable s and put it over t, time, to get v, or our speed. And speed is simply a proportion. It's just the rate of how much distance you have covered over a certain period of time. If you rearrange that equation, you will get s equals vt, which, as I may have mentioned before in our uncertainties video, is a linear relationship. Speed and time are linear. Now, just like distance and displacement, speed has its vectorial component, because speed is scalar, while velocity is a vector. Now, how will you remember this? It's alliterative! Speed scalar, velocity vector. It's great. However, they do have the same variable and the same equations. However, often when you see the equation for velocity, you will see a little delta right there in front of that s. Now, what does that delta mean? It simply means change. Displacement is a change in distance. It's you moved from point A to point B. So thusly, we put the delta. And that's the main difference there between velocity and speed. One's a vector, one's a scalar. Velocity will always have direction. Always put direction with your velocity. However, unlike displacement, there are two distinct types of velocity. Your average velocity, which I'll put v of avg, and your instantaneous velocity, v of inst. Now, your average velocity is going to be your change in distance, your change in displacement, over a change in time. Like, let's say if you're driving a truck 5 kilometers over a time of an hour. Your average velocity is going to be that 5 kilometers over that entire hour right there. Meanwhile, your instantaneous velocity is going to be your change in distance over a specific instance in time. So let's say your velocity right there, let's say that's 25 minutes into your journey. You'll divide it by 25 minutes instead of that entire hour. And that's the main difference between instantaneous velocity and average velocity right there. Now, constant velocity gives us, usually, that's what we'll be dealing in physics, a constant velocity. Velocity that never changes, which allows us to branch right into acceleration, or a little lowercase a, which is, most simply stated, a step up from velocity. It's like velocity's older brother or something, which is the change in velocity over the change in time. Acceleration is measured, I forgot to mention this, velocity is measured in meters per second. Well, how do you get that, you may ask? Well, if it's displacement, which is measured in meters, over time, which is measured in seconds, meters per second. Well, if velocity is measured in meters per second, and time is measured in seconds, acceleration is measured in meters per second squared. And thusly, we have our acceleration. Now, acceleration does not have a scalar counterpart. It is always vector, and it will always have direction, so you want to keep note of that. Now, moving on. We've got all these values. What do we do with them, you ask? How are we supposed to calculate them? How are we supposed to find them? And the simplest way to do that is a group of equations that we call SUVAT. It's a fun name. What does SUVAT stand for, you ask? It stands for SUVAT, which is displacement, your initial velocity, which is your velocity at the start of the time period that you're measuring, your final velocity, your acceleration, and your time period. And using those 5 variables, we can come up with a variety of very, very useful equations. The first one is for average velocity. Your VAVG is going to end up equaling U plus V over 2. Now, you're probably wondering, how in the heck world did I get that? We also know that it equals S over T. This, right here, is simply yielded from the fact that if you take the mean of your initial velocity and your final velocity, you're going to get average velocity. Your mean is an average. That is a mean right there. So, another equation that we can use is, let's get acceleration. We know our acceleration is our change in velocity over time, correct? So if we can extend that, expand it if you will, we can get our final velocity over our initial velocity, minus our initial velocity over time. And that's another one of your SUVAT equations right there. A equals V minus U over T. Now, how about, if I just wager you something here, how about we combine these two equations? I know that's kind of scary, but let's just go ahead and do it. We're going to end up getting something along the lines of displacement equals U plus V multiplied by T over 2. So now we know how to find average velocity, displacement, and acceleration. We're trying to find all our variables here, so why not? Let's just find velocity too. So if we rearrange this equation right here to find our final velocity, we get V equals U plus AT. There we go. And then, if we want to rearrange it again to find time, we get T ends up equaling V minus U over A. Bam! Now, we can find pretty much any of these variables with just those equations. But there are also just a few more useful equations. Yes, equations. It's what physics is made out of. Equations after equation. There's just 2 more equations that we can use. Just, let's say you want to find your final velocity, but you don't have the time. Because, I don't know, physics problems tend to do that. You can use this equation. V squared equals U squared plus 2AS. And how about you want to find your displacement, but you don't have your final velocity? Well, then we use S equals UT plus 1/2 AT squared. I write that down. I write it down with all of our other equations that we've compiled. And those are your Suvat equations. They are the key to solving any motion mechanics problems involving linear motion that you may ever see, ever, in your entire physics career. That is the key right there. So, now that we've covered that, let's cover some basic things when you're using the Suvat equations. For instance, signs of measurements for displacement and velocity, because they're vectors. And thusly, let's say you're moving at 1 meter of displacement, and negative 1 meter of displacement. Now you say, but Lucas, you can't move negative 1 meters. That's impossible. Well, it is. In physics, when you have a negative, that means you're either going left or down, relatively. Now you see, in physics, we like to talk about relative frames of reference. And what that is basically based on what you're seeing. Now, if I'm looking at something and I'm moving left, I can arbitrarily slap a negative on that something because it just makes it easier to calculate. And that's what physics wants you to do. It wants you to apply negatives to certain things and positives to up and right, so that it just makes it easier to calculate when you're using vectors that involve direction and such. The same is true for velocity. 1 meters per second and negative 1 meters per second. That just means I'm either moving up or right at a meters per second, and for this one, down or left. Now for acceleration, it gets a bit more complicated. Yes, we still have the up or right and down or left thing, but because acceleration is a rate of change of a rate of change, it can also mean, if you have a positive acceleration, that your velocity is increasing. However, if you have a negative acceleration, your velocity could be decreasing. How do you know, you may ask? You don't. The problem will probably tell you. If it doesn't tell you, then you don't have to worry about this stuff. And thusly, that covers the signs. And now there's one more thing we need to cover before we just go ahead and ruin everything and apply graphs. And that is free fall. In physics, we love free fall. When things are falling freely in the sky, we cheer with jubilation, even if it's a person jumping from a skyscraper, because it makes for good physics. And thusly, when a problem is acting in free fall, the acceleration always equals little g. Now what is little g? Little g is the gravitational field of Earth. Now we have an equation for that, but I'm going to cover that in a later episode. For right now, all you need to know is it's 9.81 meters per second squared. Know that number. Learn that number. Love that number. Have children with that number. Don't have children with that number, that would be creepy. But know it, because that is the key, because you will see many, many problems where they just say an object is falling. For example, let's do an example problem with Suvat equations. Let's say a ball is dropped from 5 meters in the air over a period of 2 seconds. Now, can you tell me the velocity? Pause the video and try to solve it for yourself. If you just want me to do it, keep watching. Now, you're probably thinking, if you kept watching, you didn't solve it. We only know the displacement and the time. How are we supposed to figure that out? It didn't give us anything. Well, that's where you'd be wrong, because even though this problem looks like it's not giving you anything, it's actually giving you everything. So, we know that our displacement, our s, is 5. Because it's down, we'll make it a negative 5. And we know that our time is 2. But we also know that it's falling. It's in free fall. So our acceleration is 9.81 meters per second. In the negative direction, it's going down. But it's also speeding up. So I'm going to make it positive for this instance. And because it was dropped, our initial velocity is going to be 0 meters per second. So now the only thing we don't know is that final velocity right before it hits the ground. And using one of our many Suvat equations, we could easily solve this. I'm just going to pick the one that's v squared equals u squared plus 2as. So, if we solve for this, what is u? It's 0. What's 0 squared? 0 squared is 0. The whole term is just canceled out. And now we've got 2 multiplied by your 9.81 acceleration multiplied by your negative 5 meters per second equals the square root of v. If you whip out your handy dandy calculator, my trusted TI-84 plus CE, you ended up getting 2 times 9.81 times negative 5 equals negative 98.1. You take the square root of that wonderful number, and oh my gosh, you can't! You can't take the square root of a negative number and have it be a real number. Oh my gosh, where did we go wrong? Well, if you were smart and you were watching, you caught it. I made this positive. It's negative. We're moving down. I said that things moving down should be negative, so I need to make sure that everything in a downward direction is negative. And thusly, we apply a negative here. And so, if we take the square root of just 98.1, our velocity ends up being 9.9 meters per second. And there you go. That's how you solve a Suvat equation. But it's not over. No, the horrors of physics never cease, for now we add graphs. There are 3 standard types of graphs that we can have for motion, and I like to think of them on levels. Level 1 is a graph of displacement over time. Level 2 is a graph of velocity over time. And level 3 is a graph of acceleration over time. How do you rate these graphs? It's pretty simple. Let's say you've got a straight line here on all of the graphs. Let's discuss what a straight line means on all of these graphs. On displacement versus time, it means nothing's happening. Your displacement is remaining the same. So therefore you aren't moving. You're not moving at all, you're just standing in one spot, and it's really boring. Now, however, if we go up to velocity over time, this means that you are moving at a constant velocity. If we go up to acceleration over time, it means that your acceleration is constant. Therefore, your velocity is increasing, and your displacement is increasing exponentially. Speaking of that, if we had a straight up linear line here on our displacement versus time graph, and a straight up linear line here on our velocity versus time graph, this means your acceleration is your displacement is increasing at a constant rate. That means you have a constant velocity. This means your velocity is increasing at a constant rate. That means you have an acceleration. Now, if you have a wacky exponential curve here on your displacement versus time graph, that means that your displacement is increasing at an exponential rate, which means that your velocity is increasing at a constant rate, which means you have a constant acceleration. That's why there are levels. On acceleration, you're only ever going to have a straight line. Anything more, and it's crazy. So don't even bother. Now, there are a few properties that we can list with this. And the properties are the slope of the line. Let's say if we have a straight line here, the slope of the line of the displacement versus time graph is your velocity. And the slope of the line of the velocity versus time graph is your acceleration. In the same way, the area under the acceleration over time graph is your velocity, and the area under the velocity versus time graph is your displacement. And that's why I like to see them as levels. Because you can level up from your displacement from time graph, you find the slope, you get your velocity, and level up to a velocity versus time graph, find the slope of that line, get your acceleration, and level up. In the same way, you can level down. Find the area under your acceleration versus time graph, that's your velocity, level down. Find the area under your velocity versus time graph, displacement, level down. And that is pretty much it for graphs. I know, it was kind of scary, but now that you know, you know. Oh, and one more thing. Sometimes your graph might have an extended y-axis. Oh, no! Now, what does that mean? It just means you have negative numbers, which, of course, in the case of a displacement versus time graph, just means you're going down or left. Velocity versus time graph, down or left. Acceleration versus time graph, kind of complicated. You could be going down or left, or you could be decreasing your velocity. It all really depends. And, thusly, you're going to need a stronger explanation. It'll probably tell you in the problem. And finally, we have one last thing to cover here, which is projectile motion. You may have noticed that all the problems I've been discussing so far, we've just been moving in straight lines. The unfortunate problem is, things don't really move in straight lines here on the planet Earth. We move in weird curves. For example, projectiles. Let's say you're throwing a ball. it moves in a parabola. Now, in order to analyze the projectile motion of the ball, we're going to analyze it at 3 points. Where it starts, halfway through, and where it finishes. Now, the direction of the velocity in each of these instances is going to be like that. There's going to be acceleration of gravity acting downward on them every time. Here's our full horizontal displacement down here, and here's our full vertical displacement up here. Now, we can organize this. Let's draw all our variables. In our instance of our horizontal components, we've got at time 0, our displacement is 0, or our displacement in the x direction because it's horizontal. Our velocity is going to look something like this. That's a line. We're finding our horizontal component, as I discussed in the vectors video, and thusly it will be our velocity right here. This is line v times the cosine of the angle, or theta. We always use theta for angles. And our acceleration at the moment will be 0. At time equals 1/2, or t over 2, our displacement is going to equal our full horizontal displacement over 2, and our velocity is going to equal v cosine theta once again, and our acceleration is still going to be 0. Think about it. We're not accelerating in the horizontal direction, we're just moving forward. Gravity acts vertically, and thus it will only apply in the vertical direction. And once we get to t equals t, s is going to equal s, v is still going to equal v cosine theta, and acceleration is still going to be 0. What can we glean from this? Well, we can put it all together in an equation to just find that. Our s of x is going to equal v cosine of theta times t. It's your simple equation for velocity. Displacement equals velocity times time, or velocity equals displacement over time. And that's one of the useful equations for projectile motion. Now, if we take it on the flip side, and we find our vertical components, we look at t equals 0, our displacement, once again, is going to be 0. Our velocity, because now we're doing vertical, is v sine theta, and our acceleration, for now, is negative g. Because gravity always applies. It's always accelerating you. Right now, you're sitting in your chair watching this video, and gravity is accelerating you at 9.1 meters per second squared towards the center of the Earth. It's only the ground that's stopping you from rocketing downwards into oblivion. So be thankful for that ground. Now if we go to t equals t over 2, our displacement is going to equal the height, because if you think of our curve, that's where it's at the top of our curve, the top of our parabola, if you will. Our v is still going to be, v is going to be 0. Why is that, you may ask? Well, think about it. If you throw a ball into the air, at the top of that parabola, it briefly stops, where the force of your throw and the force of gravity become equal and counteract each other, right before the force of gravity becomes greater and pushes your ball down. And therefore, the velocity is 0. It stops for an instant, and that instant is the instant that we are studying. Our acceleration is still going to be negative g. And finally, when we get our t equals t, our displacement's going to be 0 once more. Our velocity is going to be v sine theta again, and our acceleration is still going to be negative g. Now, what equations can we gain from this that end up being useful? You can end up making several equations, but most of them will just say 0 equals 0. The two that are quite useful in this instance, let me write down that one that we came up with before for the x so you can see them all here. The two that we come up with is the height, or the vertical displacement, will end up equal the velocity squared multiplied by the sine of theta squared over 2g, and time equals 2v sine theta over g. And once again, it is just simply our Stuvot equations, where we have our displacement equals our initial velocity, which is 0, over our final velocity right there, over the 2 acceleration. And the same thing, except slightly rearranged to account for time. And those are going to be your useful equations for projectile motion. But we're not done yet. There's something creeping up in the corner that's going to ruin all of your projectile motion problems. Air resistance. Air resistance is the bane of physicists everywhere, which is why, as you will see, in most of the problems that you will be given, there will be that nice little note on the end that says, neglect air resistance. But it's a good thing to always check, because if there is something that says air resistance, you're going to have to scroll down our videos list and go all the way down to the part where we talk about air resistance. It's going to be complicated and it's going to suck. So, pray that all your problems will say to negate air resistance, and thank you for watching!